Congreso Internacional de Energía, esperando que tanto las ponencias como los talleres estén siendo de su interés y logren consolidar todas las dudas que surjan en el trayecto. El día de hoy iniciaremos dándole la bienvenida al doctor Kamaljit Singh con la ponencia Interacciones Roca, Fluido. El doctor Singh nos visita de Reino Unido y es profesor de la Facultad de Ingeniería y del Departamento de Ingeniería y Ciencias de la Tierra en el Imperial College London, investigador con una sólida formación en flujo multifase en medios porosos, microtomografía de rayos X, procesamiento de imágenes en 3D, física digital, reconocimiento internacionalmente con publicaciones en revistas de alto impacto. Welcome.
Thank you very much for the kind introduction. I didn't understand very well, but I'm sure it's inside the right way. Welcome to my presentation. I'm going to give you some overview of my research I've been doing for the last few years, which you can see from the topic, which ranges from rocks to termite nest, which looks like it's very different topics, but I'll try to show you there's some similarities, and main idea is like the tools we are developing for petroleum engineering can be utilized to answer some sort of biological problems, fundamental problems. This is what I'll show you towards the end of my presentation. But most of my research is focused on two-phase flow in porous media, which has many different applications. Okay, so the first one actually I have listed here is CO2 sequestration. We were part of the center, which the project finished 10-year project finished in December. Mostly looking into the sequestration of CO2. So the idea is because the CO2 is increasing in the world, so what the idea is to capture it from the industries and pressurize it, inject it underground. Either you can inject it into saline aquifers, or you can use the depleted oil fields, because we know the geology of these ones, and you can pressurize it, inject it underground, and you can have a lot of different processes here. The first, you can look into reactions. So when CO2 goes in, it mixes with water. So what it does, it makes a carbonic acid. If you inject it into carbonates, so I need to speak here, sorry, okay? I hope I can interact with you guys. You can't see my hand movements very well. Well, I'll try to do it, okay? So the CO2 mixes with water, it makes carbonic acid, and it can dissolve carbonate rocks. So there are other reactions also going on. It can mix with, let's say it's injected, it can mix with water, it gets heavier, and then it can sink. So you have some gravity fingers. But today our focus is looking into, let's say when you inject CO2, what it sees water, it pushes water, and so let's assume very simple system is a two-phase flow system. Okay? And the second application, which is important as well, if this thing works, I will show you. Okay, so in petroleum industry, so what we are looking into, what we are interested in, can you hear me? Sorry about all the hiccups. Now? Yeah, okay. So what we are interested in, let's say your oil is sitting in the reservoirs. The interest is you make a well, you make another well, very simply you inject seawater. Seawater pushes oil. Again, it's a two-phase problem, right? It's a miscible fluid flow problem. And also, there's another one, which is related to contaminant transport. So let's say if you have spill, which is very common, and also especially at the airports, if you go at the airport next time, you see a lot of patches of oil there. So oil can leak while filling. Because of gravity, it can percolate downwards until it sees a water table. Because it's lighter than water, so it will stay on the top. Due to fluctuation in water table, it can get mobilized or trapped. So this is again a two-phase problem. But there are many examples. If you have rain, the water percolates downwards, it's also a two-phase problem. So there are many factors which can affect this two-phase problem. the densities, viscosities, and one of the main factors is the wettability, which is studied for decades, but I think, according to me, it's the least understood topic. We are working a lot on it. So the wettability, just to define if you're not familiar with these terms is, so let's say if you have a solid, and you put a droplet of water in this case, and at the three-phase contact line, you make a tangent and you get the contact angle, this is called the contact angle. If it's less than 90 degree, we say it's a wetting surface. If it's more than 90, it's a non-wetting surface. And you can define a little bit more expanded way. You can have a completely wet surface, the water wet neutrally at 90 degree, or your oil wet or completely oil wet. But you will see many different definitions in the literature, but the idea is, let's say, keep it simple. More than 90 or less than 90 degree is a wetting or non-wetting system. In many disciplines, it's also called hydrophilic because it loves water, and or hydrophobic if it hates water. Okay, the same things. Okay, so this is an example. You might have seen after the rain, you see the leaves and you see the water droplet on the top. So they make a spherical surface. If you measure the contact angle, it ranges from here to there. You can say it's a hydrophobic system. But there are some plants, let's say lotus and many other plants, their nature, their surfaces, they are all wetting, they're hydrophilic, but they still make these droplets. The reason for this one, because these are rough surfaces. And because of nanoscale roughness, they can form the droplets because the interfaces are wetting, but they're pinning there. And they can make hydrophobic system. And they utilize it. When it rains, it makes the drop, and the drop rolls over the leaf. And what it does, it takes all the dust and dirt particles away. So it's useful for the plants. And you see all things, wettability in nature all the times. For example, you might have seen the water strider running on water without sinking, right? If you look into the microscopic view of the legs, you see hairy legs here. So it utilizes this thing along with the surface tension properties of the water. And the water can't, let's say, invade in the legs. And these legs, all they are filled with air, so they make it buoyant. It can just keep running on the water. And also ducks, why don't they sink? Because they leave some sort of oil, and it's an oil-wet system. Water doesn't go and penetrate into it, so they don't sink. In technology, there are a lot of different examples. And this one here, for example, if you want a raincoat or rain suit, you want some air breathing in as well. But you want to make the properties so that water doesn't go in. So you would like to make it hydrophobic, right? So the materials are made hydrophobic so the water doesn't go in, so that you don't get wet. Although if you have a lot of pressure of water, if there are droplets, water can invade in. I'll show you later during my presentation. And other things which I gave example yesterday, if you're wearing leather shoes and the water comes and you see they get wet. But sometimes what you do, you buy a spray and you spray on the top of shoes. What you want to do, you make a hydrophobic system so the water doesn't go in your shoes. So these are many examples you see in nature and technology all the times. Okay, how do we measure the wettability? Traditionally, yes, thank you. Traditionally, what we have is called the goniometers. What we interested, let's say we are interested in some sort of flat surfaces. So we put our flat surface on the top of this plate, shine the light through, and then there's a camera. Camera records the images, and you can define the contact angle. Let's say in this case is a droplet making hydrophilic system, and this is a hydrophobic system because the surface is treated. Okay, so this one is okay, but when it comes to 3D, it's not the represented system using the flat plates because the rock is complex. It has roughnesses, there are many other factors, different minerals. So what we want to do is we want to measure the contact angle in situ, inside the rock. I'll come to the point where how do we measure, how do we really capture these images. So there's a small video which was captured by one of our PhD students in the group, previous one. So what you see here is a rock, it's called Catton. It comes from a small village in the UK. It's a carbonate rock, and we have done some experiments. We conducted experiment with CO2, and black you see CO2, and this is the water phase. And this video is going to show you some image processing plus also how we measure the contact angle in the system. So what we are going through the horizontal cross sections. First we filter the data so that the noise is less, and then we binarize it. We segment the phases so that we can do some analysis on it. So this is like labeling 1, 2, and 3, or 0, 1, and 2. And now we separate out the CO2 droplets, or what we call oil CO2 ganglia, and then what we can label it, which means different colors for different disconnected components of CO2. And we can choose, let's say I'm interested in measuring contact angle on this droplet. We zoom in, either we can do the straight way if the resolution is good, or we can capture another image, and we do the same processes again, filter it, binarize or segment it, and also we can make some sort of surfaces out of it to visualize in 3D. You'll see in a second. And the idea is now to capture the 3-phase contact line here. And if here you see it's a 3-phase contact line, now we bring the original data on the top of it. Original data means a grayscale image. Now the whole point is to make a surface which is perpendicular to this 3-phase contact line. This is the trick here. So we do it manually. We look into some places where it is perpendicular to the 3-phase contact line. And there we measure the contact angle. Here in this case measured to CO2, but in generally petroleum engineering, it's measured through the denser phase. But in physics and many other disciplines, they do measure from different phases. So but mostly in petroleum engineering, it's measured through the denser phase, to keep it simple. Now, because it's measured through CO2, we subtract it from 180. Then it gives us a contact angle. So this is the way what we do manually, but if you want to do like hundreds or 300 points for statistics, it takes like weeks or 2 weeks or so. It's really labor intensive. So we had a nice student for masters for 3 months. He did automatic, made the method automatic, and we published a paper on it. And exactly the same principles if you have a droplet, and we create some sort of small subsets, and we can scan the whole surface, and you can measure the contact angle everywhere here, on all the surface. We're getting thousands of points here. So you can get more information about the variability automatically from the system. Now, so far, although this is designed in our group, but there are a few other groups working on this. So this is on droplets or trapped phases, which is what it gives you equilibrium contact angle. But when we are looking into fluid flow, it's not in equilibrium anymore. So either it's moving, either CO2 is pushing the water or water is pushing CO2, and these angles are different. Because if you want to model the system, you can't use the equilibrium contact angle. So either, let's say this is your equilibrium surface or interface, and if you move it this way, then you have a larger contact angle, it's called advancing. If you're moving the back phase, you can have receding contact angle. So this is important to measure in situ, and I'm going to show you how we capture those dynamic images. So we haven't done so far, but the idea is to get the dynamic contact angle so we can feed the models correctly. Okay, so these images, I will talk a little bit about how we really capture those one. We use a device called X-ray microtomography. This is very similar to what you see in hospitals, like a CT scanner. When, for example, if I want to scan my brain, so the patient goes into the machine and all the things revolves around you, you see the scary noises. But what is happening, so the camera or let's say detector is moving and the X-ray source is moving around you, it captures multiple images. So then they make 3D image out of it. Okay? Here is the same thing. Instead of moving the cameras, here the sample, let's say sample is sitting here, this is my X-ray source, this is like a detector. My patient moves, my sample moves. Okay? So the sample moves, let's say you take one image here, I rotate, you take another, rotate another, you move by 360 and you capture multiple images, let's 1,000, 2,000, 3,000 images. Then we combine them together to get a 3D image like this. And this rock is quite tiny, it's like about 5 millimeter in diameter. And we can capture multiple one and then we stitch together to get the longer sample scanned. Now, we can also zoom in and look into the higher resolution images. And this takes quite a lot of time. It takes about, this image takes about 5-6 hours. This is the same thing we have in our laboratory, zoomed in image. And the rock, generally when we scan, because we do a lot of in situ measurements. So we put the rock in a core holder, which is made of carbon fiber. The reason for using carbon fiber, withstand pressure and temperature. The maximum we can go to 80 degrees centigrade currently, and one core holder can go to 120 degrees centigrade. And the pressure we can go to 180 bars or 118 megapascals. So these are all connected with the flow lines. We can heat it up, measure the temperature, and what it does, it puts the probe, temperature probe next to the sample, and it gives signal to the PID controller. So the PID controller controls the temperature of the outer heater. So we can measure the temperature next to the rock. We can control the pressure because all the lines, they go behind the microcity. So we can do in situ experiment. But the problem here is the scanning time. It takes about 1 to 5 hours or 6 hours depending on the resolution. So let's say my tiny rock, I conduct some experiment in terms of, let's say it's full of water. I want to inject CO2. It takes about 3-4 hours and then the experiment is done. But we can't see the dynamics here. So getting the dynamics, what we do, we utilize a facility called synchrotron imaging. So we have few synchrotrons in the world which can do this thing. So what we have, it's like a half a kilometer long ring, and some synchrotrons is longer than that. What we're doing here, injecting the electron, and what they do, they travel almost at the speed of light, and of course in vacuum. And the X-rays coming out of them, they are brilliant. What they do, instead of getting image in 4 to 5 hours, we get the same image in 38 seconds. Now we have improved it, let's say, to 20 seconds. So that means if the experiment is lasting 4 or 5 hours, it's slow enough, then we can capture the interfaces moving in the porous media. So there's an example of this. This is the same rock again, but we use in the experiment. We fill it with water, and then we inject oil into it. Now, to start with, it's a hydrophilic rock. I didn't change the property. Naturally, the rocks are hydrophilic. So the oil will go as a non-wetting phase. Okay, so this is what you see in the yellow phase. The other phases are not shown, otherwise you can't see anything through the rock. So you see it's a drainage process, and you see big jumps, right? This is the characteristic of the drainage process, which I'm going to explain in the next slide. So you see big jumps, jumps, and it progresses further until it gets the final saturation over there. So we can see what exactly is happening here. I can represent my pore space, let's say, in a triangle shape. It doesn't need, okay, let's say this is a cartoon of the pore space. Just to explain, I'm sure you guys know this thing. So let's say we have many different grains. The biggest space here is called the pore. And between the pores, the minimum constriction is called the throat. Throat is not, it doesn't have volume, it's just a surface. But a representation, we can make sometimes tubes. So the pore here, what I'm representing, is like a triangle. When the oil goes, oil is a non-wetting phase. It tries to occupy the larger pore space. So it goes inside, and you can see from the shape, it looks like a non-wetting, making a droplet shape, right? Again, but the reason for triangles, you can have any shape for cartoons, but it should not be a circular shape, because the idea here now, the oil goes in, it leaves behind some sort of water in the corners, and this water is connected throughout the rock, and this is the idea here, to represent into a system which has some sort of corners. It can stay in roughnesses, corners, smaller pores. The oil or CO2, it goes into larger pore spaces always. Okay? Now let's say there's a competition. There's a competition between my oil is going either in this or that. Let's forget about all of the pore and throat spaces. Now what's going to happen? Because it's a non-wetting surface, we can calculate the pressure, very simple equation with Young-Laplace equation. The largest throat will give a least resistance to flow here. Okay? So it will invade to the largest throat. It will jump into the pore. I was giving yesterday an example. Let's say my room is full of balloon, and there's one door. Everything is big here. Door is small. I'm pushing the balloon. Balloon makes a shape like a oil, right? I'm pushing the balloon. It doesn't want to go. But once like this is entry pressure, it needs to be entered into that throat. So once it's entered, then it will jump. It can jump multiple pores depending on the properties of the next throats. If the next throat is, if all the throats are smaller than this, it will stay here. if the next throats are larger than these ones, it'll keep going. That's why you see big jumps over there, right? Okay, so this is the one thing, and in oil industry or in chemical engineering as well. So this is one representation of the same story. So what we're looking into is a capillary pressure versus saturation of wetting phase. It doesn't need to be wetting phase, it can be not wetting, but traditionally it's a wetting phase, so it's better to keep it consistent. So we have saturation of wetting phase in this side, let's say full of water, the rock is full of water. Now I inject oil into it. As I said, oil is a non-wetting phase. Let's say there's a competition between these two throats. And this is the largest one, so the oil will go from here, it invades. It's like a balloon, again, the same story. But you need a pressure to go through this door. So you build up the pressure. You need entry pressure. When you occupy this pressure, it jumps. It fills this pore completely. And then it waits for the next throat, then it makes entry pressure again, and then jumps. So typically you see the curves like that, but they are more smooth. This is just a cartoon of it. So this is what traditionally what we generally plot it, but this is the whole concept is behind this is controlled by throat sizes here. Okay, the drainage process in water wetting system. But when we change the wettability, we'll come to that point. One more process which is happening, it's called the roof snap off during drainage. So what's happening, let's say this is my oil at the first time step. In the next time step, what can happen? It can jump from here or there. There are two throats, let's say. And this is the larger one, so it should jump from this one. And now, when it jumps, it releases, let's say it's a lot of dissipation of energy. It needs to jump and it equilibrates only next to the throats. It needs all the volumes to go into this throat. So first, the volume where it comes from, my flow rate is so low, it has to come from somewhere. So what it does, it's not any local process anymore. It gets the fluid from the neighboring throats. You see this black spot, it's the previous step, and the red here is the next step. So it gets the fluid from neighboring throats and then fill this next pore. But during filling here, there's a disequilibrium pressure. And due to layer flow, it just cuts it off. I'll show you when I explain the water flooding system, then explain what it means by the snap-off process. So this is interesting, and we've been exploring few things because it depends on the geometry of the rock. If you have glass beads, let's say sphere packing, you won't expect this sort of behavior. Okay, so we've seen the drainage. Now, in drainage, it pushed the water out of the system. But as I said, the water is still connected. It's about 56%. And then the rest of the phase is water phase there. It's all connected. Now, if I inject water from the base, I call it secondary imbibition. Generally, it's an imbibition. I call it secondary imbibition because the water is already present in the system. If let's say, for example, if the whole system was full of oil, I inject water to displace it. If it's imbibition, it's water wetting case, that imbibition I would call primary imbibition. Just this the terminology, but it's the same thing, okay? The secondary imbibition, that means I have some water present in the system and I flush it from the base and then I look into how the displacement occurs. And you see now, I'm displacing oil from the base. I inject water. And now you see, it's pushing. The steps are not bigger anymore. It doesn't jump big, right? The reason here is because the imbibition is controlled by pore sizes. Energy dissipation is less compared to throat. It's not a balloon anymore, okay? So you see, it's going slow, one step. And there's another difference is all the oil doesn't go back. It leaves behind some trapping over there. It's called the trapping of the oil, could be CO2. And this is the final state after complete imbibition. It takes about 1 pore volume, means the volume of the pore space in the rock. If it's a 1 pore volume, it doesn't take much water to get to the final saturation. Different colors here, they are disconnected component of oils. So under the same flow rate, they will never mobilize. So what you need to do, either you need to increase the flow rate or change chemical properties or mix some soap in your water or surfactants so that you can change the properties of this. Okay, so we can see what's happening, exactly the same cartoon. So you have drainage process happened, oil sitting into the larger pores already. Now you start water imbibition. What's going to happen? The water because it's connected, is going to swell here into the corners. It will not mobilize because it's pinning the surface here. You will get a hinging contact angle, but as the flow is going, then you get some advancing contact angle. When you reach advancing contact angle, this interface is going to move. Okay? It's in the pore space, and the same story you have in throat. Let's say this is my throat surface between two pores, and if you make the cartoon, it's the same cartoon, it's the layer, what we call is a water layer swelling. The water in the corner swells, and when, let's say, these two interfaces merge, then you get disequilibrium of pressure. What it does, it just snaps it off. Okay? It's the same thing. So what we can do, we can also calculate just based on simple geometry. So if we can assume, let's say this is the square or triangular pore, and with very simple geometrical principles, we can calculate what's the pressure required to get this snap off. Okay? And also there's a condition, we can also find the condition at what contact angle you'll have the snap off in these idealized pores. Okay? But of course, in reality, things get more complex. So we need to do some sort of advanced modeling.